So this is problem 6.16 out of Griffiths' Introduction to Quantum Mechanics, edition 3. I'm going to work through this, and before I start, I'd really appreciate it if you could please like the video and subscribe to the channel. I'll be uploading more videos like this, so if you're interested in this or you're going to have a class in this, it might be a good idea to subscribe and have these resources available for you. So the problem says, working from equation 6.33, which I'll grab in a second, find how the vector operator v transforms for an infinitesimal rotation by an angle delta about the y-axis. That is, find d, the matrix D, in v prime equals dv. So equation 6.33, that's the first thing I'm going to write down. And that's L sub I, v sub j is equal to I, h bar, and then the Levy savant. Okay, so this is 6.33, we'll need this. And then I'm just going to draw a little picture here. So this is, we'll call the z-axis, which is where we're normally rotating about. We'll call this the y-axis, this the x-axis. So normally we rotate about z. That's very common. But in this problem, we're rotating about y. Okay? So there's a symmetry about y that'll be kind of important to make note of. The other thing that's important to make note of is that our rotation for y for a small delta. So this was done in the book. Hopefully you're okay with this. And it's very similar to other operators that have been done in chapter 6, so nothing new here. We find that the rotation operator can be expressed like this. Now, because of this symmetry, we can say that y equals y prime. So there's no transformation about the y-axis, just like if it was the z component, z would equal z prime. Now, how do we find the transformed coordinates? We'll start with x prime, and we just use the fact that our rotation operator, dagger, x times r, these are operators. And, well, we know what that is. This is our rotation operator, so if we do a complex transpose, that's just going to be 1 plus I delta over h bar L sub y x hat, and then of course just what we have, not complex conjugated. Okay, so we have to be careful multiplying because these are operators, so we have to be very careful with the order, but we'll get our transformed x being equal to x minus I delta over h bar xly. So obviously these are constants, so the operators don't really do anything to it. That can go out front, but these you have to be very careful with. The order matters. And then plus I delta over h bar. This time ly goes first. And you're going to have more terms, but the important thing to know is that delta is very small. So delta squared and up can just be neglected. So this will all be just zeros for all intents and purposes. Okay? And the important thing to know here, just to rewrite this, is this, is plus I delta over h bar, those constants. And hopefully you see this is the commutator relation, L sub yx. And we know what that is from the equation that they referenced in the problem. This is going to be I h bar. So with the Levy savant, hopefully you're okay with when this is plus 1 or minus 1 or 0. We're really summing it, but so because we're going from y to x, we're going backwards. This will be a negative, and then our v will be in our other component, or z component. And I squared is negative 1, so this is x plus the h bar drops delta vz. Okay, y component we've already done, and there's really no difference between that and what we're going to do for the z component. It's actually basically the exact same thing. So I'm going to go by, really I think I'm going to skip a lot of steps because it didn't really matter if I treated this as x or z or whatever. So essentially you're going to get z hat plus I delta over h bar and this commutator relation. The only difference now is the Levi-Savant is going to change signs. So before we were going from x to y, so that became negative. So now you're still going to have your I, you're still going to have your h bar, and it'll still be v sub x. But because we're going from y to z, then we're going to have a positive here, and the I squared makes it negative. Hopefully that makes sense. So minus delta vx, and everything else cancels as before. And now we can go ahead and put this down into our matrix form. We have all the components we need. So the way that we're going to do this is v prime equals dv. So v prime are our new coordinates, x prime, y prime, z prime. We're going to have this matrix here multiplied by x, y, and z are unchanged. And if we think about what this needs to be, if we try to multiply this matrix here, well, we had an x, so 1, nothing about the y, and delta. So if you multiply this, this is just x plus delta z, which is what we wanted. For y, that's really easy because it doesn't change. So the x and y are 0, or the x and z are 0, the y is 1. And same thing here, the x component will be minus delta, 0, 1. So if you were to multiply this out, you would get the relations that we just found. So this is your v prime. This is what they wanted, which is your matrix D. And this is your original v. So hopefully that makes sense. If it did, please like and subscribe, and I will post more